Today's topic is blackbody radiation in the Planck distribution. Now, we've already used Bose-Einstein statistics to derive a special case that is used for photons. And that is a way that we now explain blackbody radiation. But in 1900, that was about 25 years before Bose-Einstein statistics came along. And this notion of how to explain how bodies radiate as a function of temperature was still a rather unknown question in physics, and a perplexing one. It was particularly vexing because by 1900 you had Maxwell's theory of electrodynamics, you had Newton's laws, you had Newton's law of universal gravitation. And it's not that people thought physics was completely solved by then. That wouldn't really be true, although I've heard it said that, but it isn't true. But people realized that there were these nagging problems that their physics at that time couldn't solve. And blackbody radiation is one of them. Here's how it goes. All bodies radiate electromagnetic energy of some type. Even we humans radiate. Most of what we radiate, of course, is in the infrared. But all bodies radiate. And so even eminent scientists like Boltzmann and Kirchhoff and Wien and others were trying to find a mathematical relationship between temperature and how much a body radiated. And they weren't successful. But in 1900, Max Planck discovered the correct relationship, and his work is now referred to as the Planck blackbody radiation law, which we will derive in due course. The amazing thing is he had to do it in a very difficult way. There were two previous theories that we'll discuss that failed at two different one at long wavelengths and one at short wavelengths. What Planck did was find a way to merge the two together and find a way for those in-between wavelengths or frequencies to work. And his answer was correct. It matched the experimental data. At the time, he didn't know why it was correct, though. And that's where the story gets interesting. Let's talk about the problem, and let's see how we might go about trying to solve it. So if I heat an object, it will emit radiation. As an example, let's take an old-fashioned stove with a metal heating element on it. When I first turn it on, the radiation it emits is infrared. If you put your hand near the burner, don't touch it. But if you put your hand near the burner, you feel that it's getting warmer. That's infrared radiation. The heating element still looks the same. As you get to about 550 degrees Celsius, you're going to see that the burner glows a dull red. At about 700, that color becomes more bright red. As the temperature continues to increase, it will go from red to orange to yellow, and finally it's going to be white hot. So the radiation begins in the infrared region and goes all the way through the visible region of the spectrum. The interesting thing is at a particular temperature, the radiation emitted will always be strongest at a particular wavelength, regardless of what the element is. But what was not known is how to predict at what temperature the radiation would be strongest at a particular wavelength. Now, blackbody radiation and black bodies themselves are an abstraction, but we can use them to reasonably approximate things like the inside of an oven or even an incandescent light bulb. Just picture it as a heated cavity whose walls are maintained at a constant temperature and they're isolated from the surroundings, so you're in thermal equilibrium. And if you were to bore a very, very small hole in the enclosure, you could examine the radiation that results from what happens inside. Ideal black body is a perfect emitter and a perfect absorber of radiation. That means it doesn't reflect any radiation whatsoever. And this is true regardless of the geometry of the black body's walls. So experimental results indicated a relationship between the temperature and the wavelength at which the intensity of radiation was greatest. So at higher temperatures, the wavelength was shorter, where you'd see the maximum radiation. At lower temperatures, the black body peak was, of course, not nearly as high, but happened at a larger wavelength. So this was experimentally understood. It just hadn't been theoretically explained. First explanation was advanced by Wilhelm Wien, and it was called Wien's displacement law. And it fit the data actually quite well. So lambda max, the wavelength at which the intensity or irradiance was largest, times the absolute temperature, turned out to be a constant equal to 2.898 times 10 to the minus 3 meter kelvins. It seemed to work very, very well. And it did work, except when more and more data and experiments were performed, it was found that this failed at long wavelengths. So while it worked well, up until you got into the far infrared, then it became not functional. The prediction that we had was that the density, radiation density as a function of temperature looked like some constant alpha frequency cubed e to the minus beta f over t. As I say, this worked for short wavelength or shorter wavelengths, but failed at long wavelengths. This led to another model being advanced, this time by two gentlemen, Lord Rayleigh and James Jeans in 1900. This, again, examined black body radiation in a cavity. To do that, though, we want to make a slight detour and have a look at what exactly we expect. Suppose we have a cube, maybe a cube of side L, and imagine that it's metal and hollow, and we heat it up to some uniform temperature, T. What we expect is that there will be some accelerated motion of electrons, and of course, you have to have acceleration of charges in order to get radiation, and that's indeed what does happen. According to electromagnetic theory, though, the waves that exist inside the cavity are standing waves. And they're standing waves with nodes at each wall of the cavity. So you might have a wave that looks like this, or maybe a wave that looks like this, but it's such that you have complete wavelengths between the ends. And of course, this is in one direction, but you would expect this to happen in all three directions as well. Now, of course, we know that so we can say then that we know that the frequency of the radiation is equal to C divided by the wavelength. where c is the speed of light, the speed of the electromagnetic wave, that being the case. I can write the electric field component of this wave, some amplitude, times the sine of 2 pi x over lambda, times the sine of 2 pi frequency times time. And that would be my electric field. Now, in order that the wave vanish at the wall so that you have nodes at each wall, the condition must be that 2x over lambda has to be equal to some integer n. That way, I get the sine of an integer times 2 pi, which is always 0. So that's going to be the condition on x and lambda. That means I have allowed frequencies by the same token of c times n divided by 2 times the length of the cube. Let's just look at one dimension of this first. So if I'm in one dimension, it may be that we're interested to know how many values of n would be allowed if the frequency were to lie between f and f plus df. So how many n are allowed? We could fit 2L over c frequencies in that limit. And maybe we'll call the range n of f, and n of f df would be the range that I'm allowing. So it would be 2L over c df. I would have to multiply this number by 2. And the reason is that you have two polarizations in an electromagnetic wave. We'll derive this in a little bit. But an electromagnetic wave that moves in the x direction has a polarization in the y direction and also in the z direction. So I need a factor of 2 to account for that here. So this is fine. This is a one-dimensional case. And notice that when I do this, the frequency is not involved. The frequency of the radiation drops out. Now suppose I move to 3 dimensions. If I'm in 3 dimensions, now what I do is envision 2 concentric spherical shells. And I'm interested in how much radiation, suppose one has a radius of f and the other has a radius of f plus df. I'm interested in how much can lie, how many states can lie in between the 2 shells. Now it becomes a little bit more interesting because it's going to be proportional to the area between the shells. If I'm in so-called f space, n of f df for 3 dimensions is going to be equal to 8 pi times the volume, length times length times length, divided by c cubed f squared df. This is when it becomes a problem. The difference between the one-dimensional case and the 3-dimensional case is now I have a factor of frequency squared involved. And this will be a problem for reasons that relate to the equipartition of energy theorem, which we've done earlier in the course. Remember, in the case of a radiator, we treat it like a harmonic oscillator. Therefore, we have 1 degree of freedom for kinetic energy. We have 1 degree of freedom for the potential term, the 1/2 kx squared term. Therefore, if each degree of freedom provides an energy of 1/2 kT, then I have a total energy equal to kT. So that will be for any harmonic oscillator. However, suppose I look at the energy per volume in the frequency range f to f plus df in this sphere. We take the product of the average energy per standing wave and the number of standing waves in that frequency interval, and then divide by the volume of the cavity. So what we're talking about then is an energy density that I can write as u of f df equal to 8 pi f squared over c cubed df. This is what we call the Rayleigh-Jeans formula for blackbody radiation. Here's the problem. With photons, as we call them now, radiation in a cavity, you can have infinitely many of them. If I get 1/2 kT for every one of them, that is going to predict an infinite energy. That's catastrophic. You can't have an infinite energy. You don't open an oven and find that the energy coming out is infinite. It might feel very hot, but it is nowhere near infinite. And so this predicament was called the ultraviolet catastrophe. So while Wien's method broke down at long wavelengths, Rayleigh-Jeans method broke down at short wavelengths. What Planck did was just to mathematically find a way to relate this expression to Wien's expression and then interpolate for those wavelengths in between. What he came up with was an expression that will probably look fairly familiar. This is the Planck distribution, which we derived when we took it as a special case in Bose-Einstein statistics. It looks interesting. Not only was it interesting, it provided the right answer to the experiment. So it would predict the correct frequency for a particular temperature. The problem is that there was no physical justification for why this had to work. This was just an interpolation of two disparate theories. So Planck had to come up with a physical reason for why this might be the right answer. And he had to rely on something that he really despised, or at least he found very distasteful. That was Boltzmann statistics. He never liked Boltzmann's characterization of entropy. He didn't like the second law of thermodynamics particularly. And so, but what he was having to do is use Boltzmann's ideas to justify his blackbody radiation formula. So, what he did is this. He came up with this idea. He said, let's treat electromagnetic radiation as being comprised of discrete, indistinguishable electromagnetic oscillators. Later on, these guys were called photons. This was not Planck's word, but we use that word now. The radical assumption that he made was that you couldn't have just any old value of energy of these oscillators. They had to come in discrete bundles, and they could only be exchanged in discrete bundles. He called the bundles quanta. And if you're wondering where the term quantum mechanics came from, that's where it came from. So that is to say, energy values might be something like 0 or E or 2E or 3E, but nothing in between. That was not allowed. So he used the Boltzmann distribution with only discrete energies allowed. He was able to derive a probability distribution that, of course, is now the Planck distribution and gives the correct energy, correct answer. What that meant was, while you may have a few oscillators at high frequencies and high energies, the predominant number of oscillators would not be at such high frequencies, and then you would not have the ultraviolet catastrophe, not predict infinite energy. So this actually was the solution to this very bothersome problem. That's one good thing, but even better, it laid the groundwork for quantum mechanics, which came along in 1926. the history of this development, 1900 through the 1930s, is absolutely fascinating. I would recommend looking at that and seeing how these ideas developed over time. So we've already come to the answer. We did this when we did Bose-Einstein statistics before. So you're not surprised. This is an answer you've seen, and you know that the right way to do it is to use a statistical approach, which Planck didn't have. Nonetheless, Planck did even more good work. He was able to come up with a blackbody radiation law. Let's do that right now. So we want to derive the Planck blackbody radiation law. First, we have to determine the number of available states for a given photon in some volume V. Kind of like what Rayleigh Jeans did. Let's assume we have a photon, and let's enclose it in a very large cube of side L. And where we write the energy as h bar omega, where h bar is now the constant we attribute to Planck. We call it Planck's constant. Or you can write that, if you like, as hc times the wave number kappa. Boundary conditions, again, indicate kappa x would be 2 pi times some integer n sub x over L. Kappa y would be the same, 2 pi n sub y over L. And sub y is an integer, and likewise for kappa z. Kappa z would be equal to 2 pi n sub z over L. So the number of energy states per unit volume, each with energy E, would be d cubed kappa over 2 pi cubed. So again, we're following sort of a density of states derivation again. So the number of photons with a given energy, or kappa value in this case, would be given by the Planck distribution, which is F, in this case, of kappa, E3 kappa, and that's just the Planck distribution, beta h bar omega minus 1 d3 kappa over 2 pi cubed. Just to remind you, remember there's in normal Bose-Einstein statistics, there's a term minus the chemical potential, but we don't have a chemical potential for photons, electromagnetic oscillators, as Planck might have called them. Since we're dealing with an electromagnetic wave, we know that I can write this wave as it solves the wave equation. That's one constraint on the wave. The second constraint, though, is I can write that solution first as a plane wave, right? E naught times e to the minus I kappa x minus omega t. But the electric field vector also has to satisfy Maxwell's equations in vacuum, in particular. Del dot E equals, it's got to satisfy Gauss's law. That implies that K dot E must be 0. Therefore, it has to be that the only vibrations of the wave that are allowed are in directions that are perpendicular or transverse to the direction of propagation. So as we said before, if the wave is propagating in the x direction, it can only vibrate in the y or z direction. Those two directions of propagation are allowed. So I can write then, since I have two allowed directions of propagation, I can write this as follows. 1 over e to the beta h bar omega minus 1 dk over 2 pi cubed. And I want to know the mean number of photons per volume having frequencies. Let's move to the frequency realm in the range omega to omega plus d omega. And I can do this because I know omega is equal to kappa times c. D omega is going to be equal to c d kappa. I can make a change of variables, and I can write my distribution in terms of omega, f of kappa, d3 kappa, 8 pi over 8, 2 pi c cubed, omega squared d omega, e to the beta h bar omega minus 1. Next time we'll pick up with this. We will calculate the mean energy per volume and then integrate to get the total energy.